Now, in my mind, one of the most interesting things about the natural logarithm when it comes up in integration is how it shows up all of a sudden in these integrals of our basic trigonometric function integrals. After all, when we first encountered our antiderivatives with trigonometric functions, we recognized that if we had sine of u du and took its integral, we would get negative cosine of u plus a constant. No logarithm anywhere, right? And the same thing with cosine, right? When we took its antiderivative of cosine of u du, we would end up with the sine of u plus a constant. And again, no natural logarithm anywhere. So where are these natural logarithms coming from here? And so what I'm going to do is I want to go through and I just want to prove to you that two of these forms are going to be your natural logarithms. They will show up. And you're going to prove the other two as an exercise. So let's try this out right here. Let's start with the first one. How do we get the natural logarithm of a cosine of x in our expression tangent of x? Well, in this case, it's really a simple rewrite. We say, well, this is the same thing as talking about sine of x over cosine of x dx. And right away, you get the arrangement that we can use with our natural logarithm right here, in as much as if we replace u with cosine of x, then we know that du must be the negative of the sine of x dx. And so if we move our negative sign over and take the negative of du, we've got sine of x dx. And there's our replacement right away, right? We've got the negative of the antiderivative of du over u, which we know to be, bring it over here, which we know to be the negative of the natural logarithm of the absolute value of u plus a constant c. And well, u, as we stated at the beginning, was equal to cosine of x plus c. I'll point out that there is another form that we often express this in. We take that negative that's in front of the logarithm using our property, our power property of logarithms, right? Remember, we have a property that says if we take p times the natural log of x, it's the same thing as the natural log of x raised to the p power. Well, if we keep that in mind right here, we can rewrite this as the natural logarithm of 1 over cosine of x, and often you'll see this integral expressed as the natural logarithm of the secant of x, but we recognize that secant of x is the reciprocal of cosine, and therefore it is an equivalent expression. Very interesting. Okay, but what about this guy right here, the integral of secant of x dx? How are we getting how are we getting this natural log of this sum of a secant of x and a tangent of x plus c? Well, this one's a little bit more tricky, but actually we can use a little bit of creativity right here. For one thing, we might note that we know two derivatives that are secant of x and tangent of x, and that is that we can replace secant of x with another expression that gives us that form du over u, which is what we're looking for, right? So how do we get that here? Well, let's take on secant of x. And the way we're going to do it is we're going to rewrite this as a fraction. We're going to say, let's treat secant of x over 1 as its own expression. And the creative part that we're going to do is we're going to multiply by secant of x plus tangent of x in both the numerator and the denominator. Right, so let's do that right here. If we multiply by the quantity secant of x plus tangent of x into the numerator and denominator, how does that help us? Well, okay, carrying out the distribution in the numerator right here, right, using our distributive property. Well, that is a terrible integral there, Professor. Let's try this again. we've got the integral of secant squared x plus secant of x times tangent of x. Now, if you don't recognize those two forms, pause the video and just take a moment to look back in your book if you have a table of derivatives and try to recall where you've seen those two quantities before. I'll pause for a moment and let me give you a moment to do that. Okay, well, if you didn't see them, we have this arrangement now, because if we let u be the sum secant of x plus tangent of x, well, look at du. The derivative has to be the derivative of secant of x, which we know to be secant of x times tangent of x, and the derivative of tangent of x, which is secant squared x times dx. And sure enough, that's exactly what we have in the numerator. Very exciting. So now I've got I've got du in the numerator, right? Secant x tangent of x plus secant squared x, that dx, that's du, over u, which means that I now have the natural log of the absolute value of u plus the constant. And just making that last replacement right here, sure enough, there is our natural logarithm of the absolute value of secant of x plus tangent of x plus a constant of integration. How cool is that?